Okay, we're going to learn today a technique called U substitution. And if you'll look at your book here, it says that this technique is a method for taking the antiderivative when we have taken the derivative using the chain rule. So remember when I taught you the chain rule, I pulled out my adorable little dolls that I got in Prague. And we talked about how we work from the outside in. So you want to take the derivative of the most outside function in order to get to the next one inside. Then you take the derivative of what's inside to get to the next one, etc. So therefore, to undo this process and take the antiderivative, we have to undo our nesting dolls. Meaning we're going to now look for what's most nestled, the piece or the function that is most inside, nestled, is what we're going to have to identify first. After we've done that, we are then going to work our way back to the outside. So we're doing the entire process of chain rule in reverse. Best way I know how to teach this is to just do a bunch of examples, and then we'll start to see what the process looks like. So I want to first just remind you of the first time we saw U, and that's when I talked to you guys about taking the derivative of the function ln u. And if you remember, u was because we didn't just have ln x. We had the natural log of some other expression. And then the derivative of the ln u was always going to be 1 over that inside, that argument, that expression. And then we chain ruled on the derivative of that u. So since we're doing the chain rule in reverse, what we're going to be doing is looking then for a u and a du, and then work that process back in reverse to find the function whose derivative we have in terms of u. Okay, let's hang on to that idea. We're going to see that one in a little while again. So we have two functions here in number one. We have x plus 2, that's one expression, and then we have a base to the fifth, that's our second. When we think about if we were taking the derivative, we would be using chain rule, taking care of the outside, the something to the fifth first, and then chaining on the derivative of the inside, in this case, the base. We're doing this backwards. So that means our thing that was inside, that inside u expression, is going to be what we call u. And then we're going to be looking for the derivative of that u. Now, this one is unnecessarily easy. I know it's your first time doing one, so it won't seem that easy. But when you go back after we do them all and take a look at it, you'll be like, didn't even need the u substitution for this, and you didn't. However, what's our derivative of x plus 2? Well, the derivative of x is 1. The derivative of 2 is 0. But that was a derivative with respect to x. And we always want to say that. Our derivative of u, we took the derivative of the side u, was 1. But let's make sure we explain the 1 was actually a derivative with respect to x. So our job now is to rewrite our original antiderivative, our integral, using only u or du. X plus 2 is u, so I have u to the fifth. And then 1 dx, this guy, is our du. So we have an easy power rule antiderivative. This antiderivative in terms of u, because it's a u variable, is keep the base, add 1 to the exponent, divide by the new exponent, or multiply by its reciprocal, plus c. That's it. Now, our original problem was actually in terms of x, so we want to go back and replace our u's with x. So I have 1/6 u, which is really x plus 2 to the 6th plus c. And that's it. All right, let's do another one. Number 2. So this time, we already know how to rewrite our roots in terms of fractional exponents. So I'm really taking the antiderivative or the integral of 4x minus 1 to the 1/2. Two functions again, or two expressions. I have something to the 1/2 power, that's on the outside. But with anti-differentiation, I'm looking to identify the inside. So my inside is 4x minus 1. Now I want to identify the derivative of that inside. Remember, I'm looking to sort of put things in this form right here, where I have a u times its du. So I found the u, I am now finding the du. The derivative of 4x minus 1 is 4 plus 0, but that was a derivative with respect to x. Okay. So now I go back and I put my original function all in terms of u. 4x minus 1 is u. So I'm taking the integral of u to the 1/2. Okay. Took care of my u. But what about that du? My du is supposed to be not only dx, which I have right here, but I'm also supposed to have a 4. I have to use u and du in its entirety in this antiderivative. So that means I need to multiply by 4 in order to have du. I'm never allowed to change the value of something I am evaluating. So I multiplied by 4, but I can only multiply by the one value that lets me multiply and not change its value, which is 1. So if I multiplied by 4 to get my du, I have to at the same time multiply by a 4th, because 1/4 times 4 is actually 1. So what does that mean for what I'm evaluating? That means 4 dx is my du. Put it over here. 4x minus 1 to the 1/2 is u. So I really have left over this 1/4, u to the 1/2, and this 4 dx is du. So I've used the du and the u in their entirety, but I had to compensate for the 4 that's multiplied in there with a 1/4. Easy peasy now. My derivative with respect to u, constant multiplier of a 4th, power rule, add 1 to the exponent. So keeping the base, I have u to the 3/2. And then instead of dividing by 3/2, I'm going to multiply by 2/3, like we've been doing, plus c. Now I can cancel or reduce. 2 goes into 2 once, 2 goes into 4 twice. So putting this all together in terms of x, I have 1/6 u to the 3/2, but remember our u is 4x minus 1 to the 3/2 plus c. These start to get easier, but they all follow the same pattern. All right, let's do one more easy one that follows that pattern. Number 3. We have two functions. We have the cosine of something, and then we have the something. What's inside is the angle 7x plus 5. So that's what I'm going to call my u. Now I need that derivative of that u. The derivative of 7x plus 5 is 7, but that is a derivative with respect to x. Okay, so now we're playing that matching game. We want to rewrite our entire integral using all of u and all of du. So here's my u. I have the cosine of u. My du is the dx, but it also needs a 7. So there's my du. But if I put the 7 in order to make my du, I have to compensate by at the same time putting in a 1/7. Okay, so what does my original problem look like when it's only got u and du? It looks like 1/7, the cosine of u, and then that 7 dx is my du. Okay, I'm now going to find the antiderivative in terms of u. Constant multiplier of a 7th. The antiderivative of cosine. So the derivative of sine is cosine. So the antiderivative of cosine is sine of u plus c. Now, people always ask me at some point doing these, what happened to that du? This is a derivative of u. This symbol is an antiderivative of u. When you take the antiderivative, you've undone the derivative. They're inverse operations, so they cancel each other out. So it's gone. All right, and then our last step is to put it back in terms of x. So we have 1/7 the sine of u, which we call 7x plus 5 plus c. All right, those are our first 3 very straightforward examples using u substitution. The rest of them start to get a little trickier, so we'll make a separate video for those.